Hello everyone, and in today's video I want to go over the paper that introduced the AlexNet architecture, which was introduced in 2012. And at that time it was one of the most influential papers in the field of deep learning and computer vision. But before we delve into the details behind the paper, I want to kind of set the stage, and try to explain to you why this paper was important and what problems it was trying to solve. So the paper, first of all, addresses the problem of image classification. And in particular, it addresses the problem of training large convolutional neural networks on large data sets. So at the time, it was very hard to train large models on large data sets, and there were not many large data sets at that time. But then the famous ImageNet dataset was introduced, and this is the dataset that AlexNet was trained on. So I have some points highlighted in the paper, and I want to go over them and skip the parts that are not highlighted, that I do not think are the most important. So first of all, the architecture that was introduced in the paper achieved a top 5 and top 1 accuracies, error rates of 37.5% and 17%. And it was much better than the previous state-of-the-art models. In terms of the complexities of the model, it has 60 million parameters and 650,000 neurons. And it has 5 convolutional layers, as the paper says, some of which are followed by max pooling layers, and some are not followed by that. And it also has 3 fully connected layers. The final layer has a output shape of 1,000, which corresponds to the amount of classes available in the ImageNet dataset. So to make training faster, they used non-saturating neurons. They used ReLU, and they used a very efficient GPU implementation of the convolutional operation. So they basically used double GPU training. So they split their training into 2 GPUs, and this allowed them to train a very large model. By today's standards, it's not that large, but at the time it was big, and it was hard to train them. And also, to reduce overfitting, they introduced a technique that now is very known and used a lot, but at the time it was not introduced, so it was dropout. So the authors of the paper state that CNNs have much fewer connections and parameters, and it is much easier to train them, and it is much faster to train them. And although it is much faster and easier to train them, they do not have any drawbacks in comparison to fully connected layers in terms of image classification. So they trained one of the largest convolutional neural networks at the time on the subset of ImageNet, which is the famous dataset. They used a highly optimized GPU implementation of 2D convolutional layers. As I already told you, they used 2 GPUs to train their model to make it faster and easier to train. But the size of the network made it very easy to overfit, and they had a problem with dealing with overfitting. In terms of the dataset, they used a subset of ImageNet, which has 1,000 classes, and each has approximately 1,000 images per class. So overall, there are 1,200,000 training images, 50,000 validation images, and 150,000 testing images. Then they downsampled the images to a fixed resolution of 256 by 256 pixels, And they did it by, they rescaled the shorter side of the length. So if you imagine that they have a image that is, let's say 512 by 380, they shortened or rescaled the size, the side that is 380 or whatever I said, so the lower number. And then they cropped it and centralized it to be 256 by 256. And they did not preprocess the images in any way except for subtracting the mean activity of the training set from each pixel, which basically means this one. So let's say this is a list of pixels, basically representing the image. 1, 2, 3, 4, 5. It has a mean of 3. And if you subtract the mean activity over the training set, it will basically look something like this. So you will subtract the mean from each pixel. So 1 minus 3 is -2, 2 minus 3 is -1, and etc., etc. So now let's go to the most important thing, is the architecture. So first, they use the value activation function, which now is very popular and everybody uses it. So until the paper came out, the activation function of choice was 10H. However, 10H is very slow in comparison to ReLU. So if you look at this graph that they showed us in the paper, you'll see that the solid line is the ReLU activation function, and it shows you training error rate and epochs. So basically, ReLU achieves the same error rate as 10H, much faster. So it's like 5 times faster than 10H, which helped them basically to make training even faster. So they used ReLU. They did not introduce it. It was introduced, I think, way before, but it was not popular at the time. So this is the ReLU function. It's basically, if you don't already know the formula, it's the maximum between 0 and x, where x is the output of the neuron. So let's say you take the max from of 0 and -5, it's going to be 0, and max of 0 and 5, it's going to be 5. So, as you see, values train several times faster than 10H. Training on multiple GPUs. The dataset has 1.2 million training examples, and it's too much to fit on only one GPU. So they used 2 GPUs. They spread the network across 2 GPUs and put half of the kernels or neurons on each GPU. Also, the GPUs communicated only in certain layers, so it was not directly split into 2 parts. The GPUs communicated only in some layers, not in all layers. Now let's talk about some math. In the paper, they used a technique called local response normalization, which basically helped them achieve 2 things. And there is a formula, but I'm not gonna go over the formula myself. If you want to understand the formula better, you can find videos on YouTube. There are plenty of them. But basically, what it does is, first you have an issue with the activation functions. It's called saturation. So this is basically when output values are pushed towards the extreme ends of the activation function. So let me draw somewhere here. So let's say we take the sigmoid activation function. It looks something like that. And sorry for my terrible drawing. Yeah, something like that. So this is 0 and this is 1. So the outputs are bounded by 0 and 1. And when you have extreme values that are passed through this activation function, they're going to be very close to the end. So they're going to be very close to 1 or very close to 0. And if the model learns to output very high numbers, they're going to be saturated at high ends, and the model will have a hard time differentiating between them. So, local response normalization helps avoid this issue. First, it helps reduce overfitting by regularization, and also it helps the model focus only on the most important features in a specific region. And also, it is important to note that this technique helped them reduce their top 1 and top 5 error rates by 1.4 and 1.2%, respectively. Also, a CNN, a 4-layer CNN, achieved a 13% test error rate without normalization and 11% with normalization. So this kind of shows you how much it can help you. The next idea is called overlapping pooling. So usually it was common to use regular pooling. Pooling is basically when you take a convolution, take a feature map, and you summarize it and take only the most important information from that feature map. But it was common to use a stride of, let's say, 2 and a kernel size of 2 as well. So a kernel size was equal to stride size, and it was common to train that way. But the authors of the paper decided to set the stride less than the kernel size, and it allows you to do overlapping pooling. And basically, it helped them reduce overfitting, and it helped the model generalize better. So this helped them reduce the top 1 and top 5% error rates by 0.4% and 0.3% respectively. So now let's go over the more interesting part and the part that I'm going to implement in the next video. First, the network maximizes the multinomial logistic regression objective. It basically learns to predict the best result out of 1,000 class labels. Also, from here, the important thing is that ReLU is applied to every convolutional layer and to every fully connected layer. The first convolutional layer filters a 227 by 227 by 3 image. They actually made a mistake in the paper. They used this shape, not this one. So they reshaped their original image in the dataset, which was 256 by 256, to 224 by 224. And the first layer has 96 kernels with a kernel size of 11 by 11 and a stride of 4. So the second convolutional layer has 256 kernels with a kernel size of 5 by 5, and it is also the first convolutional layer and the second convolutional layer are followed by a ReLU activation function, then by local response normalization, and then finally by the max pooling with overlapping pooling with a kernel size of 3 and stride of 2. The third, fourth, and fifth convolutional layers are connected to one another without any local response normalization or without any max poolings. So the third convolutional layer has 384 kernels with a size of 3 by 3. The fourth layer has 384 kernels again, and it has a kernel size of 3 by 3. The third, the fourth, and the fifth layers have, I believe, a stride of 1 and a padding of 1 as well. We're going to see it in the paper implementation in the next video. And finally, the fifth layer has 256 units again with a kernel size of 3 by 3. And then the fully connected layers have 4,096 neurons, each of them, except for the final one. The final one has 1,000 because there are 1,000 classes that you're trying to predict. To reduce overfitting, they used two techniques. So they used data augmentation and also they used dropout. So in terms of data augmentation, they used image translations and horizontal reflection, and also they changed the intensities of the RGB channels. So to be specific, they performed PCA on the set of RGB pixels values throughout the AlexNet training set. So this is pretty much it in terms of augmentation. It's not a lot, but yeah, that's what they used. And they used dropout for reduce overfitting as well. Dropout is a technique that basically you set a probability, let's say 0.5, and with a probability of 0.5, it will deactivate or drop the neuron. So each neuron in a layer has a probability of 0.5 of being dropped out. And I like to think about it as, let's say you have a company of 50 people. Let's say every day when you go to work, 10 people are dropped out. Or let's say 25 people are dropped out. And basically, the other 25 people have to do all the extra work that the people that were dropped out had to do. So now everybody learns to do more work than they would have to. That's not the best way to run a company, I guess, but it is a very good way of helping the models learn. And this is how the authors of the paper explained it. So they force, adding dropout forces to learn more robust features that are useful in conjunction with many different random subsets of other neurons. So again, this basically means that they become a much more efficient worker, if you can think this way. And at test time, when you basically do inference on test data, they use dropout is not used. You use all the neurons, but you do multiply the outputs of each neuron by 0.5. This is done to ensure that like your neurons do not get kind of too confident in their results, because everybody learned to work more difficult, as I already said, and then when you use all of the neurons, kind of everybody becomes very efficient and you kind of overdo. You just do too much. So this is kind of my explanation of that. So they multiply it by 0.5, which is a reasonable approximation to taking the geometric mean of the predictive distribution produced by the exponentially many dropout networks. They used dropout in the first two fully connected layers, and they did not use it on the final layer or any other layers as well. So without dropout, their network a huge problem with overfitting, but dropout roughly doubles the number of iterations required to converge. So now let's go over the details of the training or learning. They used stochastic gradient descent, SGD, as you might know it, with a batch size of 128, momentum of 0.9, and weight decay of 0.0005. This is the formula for updating the weights. And they initialize the weights with a zero mean Gaussian distribution, which is the normal distribution, and a standard deviation of 0.01. They initialize the biases in the second, fourth, and fifth convolutional layers with the constant of 1, as well as fully connected hidden layers. And this helped to accelerate the first stage of training because it provided values with positive inputs. So because if you pass a negative input to the value activation function, it's going to output 0, which is making it harder for the model to learn in the first stages. And the other layers are are initialized with 0. In terms of the learning rate, they started off with a learning rate of 0.01, but then they divided the learning rate by 10 when the validation error stopped improving. So when they see that it's not improving, they divide it by 10. And they produced the learning rate 3 times prior to stopping the training. So they trained the model for roughly 90 epochs, and it took 5 to 6 days to train the model. The network achieves top 1 test error rate of 37.5% and top 5 error rate of 17%. And now, in comparison to the best performing before the AlexNet architecture, it was 47.1% on top 1 error rate and 28.2 on top 5. So this is a huge improvement from the last model. So yeah, this is pretty much it. You can read the results further, but basically they achieve a huge performance, a huge improvement on the performance of the model. And in the discussion later, they also say that it is possible to improve this model even more by adding more layers, and when the GPUs become more efficient, better, you can add more layers and the accuracy will even improve greater, which is true and it is proven in the future. And now we can train much larger neural networks. So in conclusion, I want to summarize that the AlexNet paper was one of the first deep convolutional neural networks architectures to be successfully applied to large-scale image classification tasks. It demonstrated the power of deep learning in capturing complex image features and outperformed traditional machine learning methods by a huge margin. They used techniques such as ReLU activation function, local response normalization, training on 2 GPUs, overlapping pooling, and dropout. So this is pretty much it. In the next video, we're going to go over the actual implementation of the paper, and you will see how to build this architecture from scratch in PyTorch. Thank you for watching, and I hope you enjoyed the video.